Ladies and gentlemen, welcome to the Shaw Prize lecture by Professor James Peebles, winner of the Shaw Prize in Astronomy 2004. May I now call upon the head of Shaw College, Professor P.C. Ching, to deliver a welcome address. Professor Ching, please.
Professor Peebles, Mrs. Peebles, Professor Lau, Professor Yang, distinguished guests, colleagues, young students, ladies and gentlemen, good afternoon. The inaugural Shaw Prize Award presentation took place in the Hong Kong Convention and Exhibition Center last night and marked an important milestone in the science community. The Shaw Prize was established under the auspices of Mr. Run Run Shaw in November 2002 to honor scientists in the areas of astronomy, mathematical sciences, life science, and medicine, who have achieved significant breakthrough in academic and scientific research or application, and whose work has resulted in a profound impact on mankind. As you all know, the first Shaw Prize winner in astronomy was awarded to Professor P. James Peebles of Princeton University for his contribution in laying the foundations for almost all modern investigations in cosmology, both theoretical and observational, transforming a highly speculative field into a precision science. We are most privileged to be able to host, in conjunction with the Shaw Prize Foundation, the first official Shaw Prize lecture in astronomy at Shaw College. This has a special meaning to us. Not only that, Shaw College and Shaw Prize have a common benefactor, but we are exceptionally delighted to witness the nascence of the Shaw Prize since the initial planning of the Shaw Prize was carried out at Shaw College, and the announcement of the establishment of the Shaw Prize was held in this very auditorium. We are grateful to Mr. Run Run Shaw for his generosity and particular concern for youth education that make possible the formation of Shaw College at the Chinese University of Hong Kong. And at the same time, we have the highest regard for his dedication and passion in the promotion of scientific advancement that make the creation of Shaw Prize feasible. And I hope it won't take too long for my dream to come true, which is for one of our Shaw College graduates to present the Shaw Prize lecture in this same lecture hall. Today, we are honored to have Professor James Peebles, the inaugural Shaw Prize winner, with us to deliver his Shaw Prize lecture on the discovery and the expanding universe. I would like to call upon our Pro-Vice Chancellor, Professor Kenneth Young, who had a brief acquaintance with Professor Peebles at Princeton some 30-odd years ago, to introduce our distinguished speaker and to moderate the Q&A section after the lecture. Professor Young, please.
Good afternoon. It is my privilege to introduce Professor Peebles and his work. P. James Peebles was born in Winnipeg, Manitoba in Canada. He received his Bachelor of Science degree in 1958 from the University of Manitoba and his PhD from Princeton University in 1962. He joined the faculty of Princeton University, the physics department there, where he has remained throughout his career. It was there that I met him when I was a very junior member of the faculty in 1972. Professor Peebles was not then, but he is now, the Albert Einstein Professor of Science at Princeton. Professor Peebles is a fellow of the American Academy of Arts and Sciences, the American Physical Society, the Royal Society of Canada, the US National Academy of Sciences, and also a member of the American Astronomical Society. Professor Peebles has received numerous honorary doctoral degrees from universities in the US, Canada, Belgium, and Spain, and has held numerous named lectureships. He received the A.C. Morrison Award in National Science from the New York Academy of Sciences, the Eddington Medal of the Royal Astronomical Society, the Heinemann Prize of the American Astronomical Society, the Robinson Prize of the University of Newcastle upon Tyne, the Bruce Medal of the Astronomical Society of the Pacific, the Lemaitre Award of the Catholic University of Louvain, the Gold Medal from the Royal Astronomical Society, and of course, the Shaw Prize in Astronomy in 2004. Professor Peebles is being honored for a lifetime of groundbreaking contributions to cosmology and astrophysics. Between 1963 and 1985, he laid the foundations for almost all modern investigations in the field, theoretical and observational. Independent of some early pioneering work, Peebles realized that the observed abundance of light isotopes required a hot Big Bang, which would result today in an observable cosmic microwave background, and this was discovered by a team at Bell Labs. The Big Bang and the cosmic microwave background have become central themes in modern cosmology. And Professor Peebles' two books on physical cosmology and the large-scale structure of the universe have shaped much of the language and the scientific agenda of the fields. His leadership and vision have been critical for turning cosmology from a somewhat speculative and perhaps not very respectable subject into the high-accuracy science that it has become today. In the last few decades, our understanding of matter and the universe has been turned on its head. We now realize that the stuff in the universe consists of three parts. First, a tiny portion, perhaps 4 to 5%, of ordinary matter. Then, much more, perhaps something like 20%, dark matter, unseen but exerting a gravitational attraction. And the bulk, 70 to 75%, being a strange dark energy, known to the cognoscenti as the Einstein cosmological constant, that exerts a gravitational repulsion. Now, Newton, who taught us about universal gravitational attraction, must be turning in his grave. Peebles' work has been critical in the understanding of each of the three components. First, his work on primordial nucleosynthesis forms a basic and main underpinning of the conclusion that the amount of ordinary matter is small, 4 to 5% of the closure value. Then his pioneering studies of the dynamics of galaxies, groups, and clusters lead to the conclusion that cold dark matter accounts for another 20% or so of the closure value. Finally, it is the study of the precise details of the cosmic microwave background, a background which Peebles predicted decades ago, that has led to the determination of the amount of dark energy, 70 to 75%. All these together have two important consequences, among many others. First, the overwhelming amount of repulsive dark energy causes the expansion of the universe to accelerate, a very surprising conclusion. Precisely such an acceleration, rather than a deceleration, has been found by two independent teams, which recently measured the rate of expansion of the universe some 6 to 7 billion years ago by observing very bright and distant supernovas. Second, the totality of the three components inexplicably add up to exactly the closure value, or very close thereto, meaning that the universe is very large and very flat. So Peebles' works, taken together, have also led to a confirmation of the idea of inflation, another major novel idea in cosmology, and in fact, a statement about the first 10 to the minus 37 seconds in the life of the universe. So all in all, we now have a remarkable and breathtaking picture of the cosmos and its history. And the handiwork of Jim Peebles can be seen in every brushstroke. So let us welcome Professor Peebles to give his Shaw Prize lecture on the discovery of the expanding universe. Professor Peebles.
Friends and colleagues, thank you so much for this very warm welcome. I am delighted to be here and really happy also to have this opportunity to share with you the excitement of a story of research in physical science. I have organized this talk around historical developments in the subject under headers that will appear any moment now. We have forgotten to raise the screen. And perhaps we have remembered to turn down the lights a touch. So let us look at the headers. What is meant by this concept of an expanding universe? What might that mean to be established? How people arrived at this curious concept? How do people make advances in scientific research? An excellent illustration. Of course, you have a concept that's meaningless to us until you have evidence that that's the way the world really is, and let us look at some of the evidence for this expanding universe. And then, most subtle of all to understand, I think, unless you're heavily involved in research, how it can be that we can at the same time be firmly convinced we understand this expanding universe and yet have many open questions remaining for you, the next generation of scientists. So I've organized this around a set of laws. One thinks of the laws of Newtonian mechanics, the laws of thermodynamics. Roughly speaking, here is a way to classify the laws of cosmology. One begins with this statement: the universe on the large-scale average is wonderfully simple. No center, no edge. The idea in its modern context was introduced by Albert Einstein, upper left, in the year 1917. The year before, he had established his great new theory of gravity, general relativity theory. Arthur Stanley Eddington, professor of astronomy, Cambridge University, on the lower left, and Willem de Sitter, professor of astronomy, Leiden University in the Netherlands, upper right, were two of the leaders in popularizing or making understood Einstein's ideas and in finding astronomical applications for them. Now, Einstein had introduced this notion that the universe is simple, uniform, no edge, no center, on purely philosophical grounds. I have found no evidence that he had talked to Professor Eddington. If he had, Eddington surely would have drawn Albert's attention to the book Stellar Motions and the Structure of the Universe by Eddington, 1914. In this book, the universe is represented in the figure in the lower right. To the astronomers of the day, the universe was a universe of stars around us, and it was clearly established by counts of stars that this system is flattened like a disk or a pancake. And it appeared to the astronomers of the day that we were pretty close to the center. I like the remark Eddington enters here: we shall not be so rash as to suppose that the mystery of the sidereal universe has yielded almost at the first attack. But as each revolution of thought has contained some kernel of surviving truth, so we may hope that one may present representations of the universe containing something that will last, notwithstanding its faulty expression. Here is the story of science. One advances by successive approximations. This is, in fact, a good approximation, but only an approximation to the real world. First, of course, we're not at the center of this galaxy of stars. Here you see, I hope, a photograph, perhaps not too visible, of the sidereal universe, our universe of stars. You see the glowing band of light. That is the integrated starlight along the plane of our Milky Way galaxy. You see that the glowing light is about the same in every direction across the sky, as if we're in the center. But you see also the bands of dark running through the bands of light. That dark is not absence of stars, but rather the presence of obscuring dust that hides many of the stars in our Milky Way galaxy. Here is an illustration from the Hubble Space Telescope of one of those clouds of obscuring gas and dust. Most of the mass of this cloud is hydrogen and helium. Out of that gas, stars are forming. In this cloud, the young massive stars that are very luminous happen to be forming on the backside of the cloud. You can see the light from them glinting off the cloud, but you can't see the stars themselves simply because the dust in that gas cloud is too thick to prevent a view of them. It is this dust that gets in the way of a clear view of our galaxy, our island universe of stars. One sees a better vision of our galaxy of stars if you go to longer wavelength. This, an image taken from space at wavelengths 3 times longer than what we can see with the naked, unaided eye. The longer wavelength is much less strongly absorbed by dust, and here you see the center of this shining island universe of stars, and you can see that we are well off the center visible in the distance. So we see that the picture people had in 1914 was an approximation, true, but of course only an approximation. This is the way our island universe is. Now, people were aware at the time that there are spiral nebulae that have somewhat the same appearance as our Milky Way galaxy. Here is the closest example. They were willing to speculate that these are other island universes of stars. And Willem de Sitter was even willing to speculate that it is the universal distribution of these island universes that is the homogeneous world matter that Einstein's philosophy required. Here is a close-up picture of this galaxy called the Andromeda Nebula for its position in the constellation of stars. You see a flattened disk seen close to edge on, called a spiral nebulae, and a good illustration of why it is called a spiral nebula is shown here. You see the wonderful whirlpool structure of this island universe of stars. You see the central part of it, and if you follow weather television, you might be reminded of a tornado or a hurricane, and there's good reason. Both are supported by rotation. Common phenomena, very different scales. For later purposes, it will be useful for me to remind you that many galaxies have a halo of older stars, you see, circulating around the disk. And that in some galaxies, the halo is much more prominent than the disk, and that in some galaxies, the disk is gone entirely. It's just a halo of old stars. I'll return to that later. For the moment, let's get back to the point that de Sitter and others were speculating about. Might it be that Einstein's homogeneous universe is a homogeneous distribution of the galaxies that are themselves island universes of stars? De Sitter was willing to speculate that this might be the case, but he was very uncomfortably aware of the fact that the nebulae are not uniformly distributed. Look at this mess. This is the whole sky, distorted and flattened out so we may see the whole sky planted on a two-dimensional surface. The absence of stars in the middle line is understandable. That's the direction of the plane of our Milky Way galaxy. There is lots of dust there, and so the view out is by no means clear. That was speculated at the time, but it was also understood that the view out the top and the bottom is pretty clear, and look at the enormous difference in the distributions of galaxies above and below the plane. In short, Einstein was introducing the most audacious assumption, totally unsupported by any evidence. Let us now look at the modern situation. Here is an illustration of the clustering of galaxies in the constellation of Coma, a distribution of galaxies that might remind you of that galaxy of stars that had no disk. In fact, the structure is very similar. This is a galaxy of galaxies. Here it is in a map covering about 90 degrees of the northern sky, looking up away from the plane, so the view is fairly clear. The overall distribution of galaxies out to a fixed limiting distance, and this galaxy of galaxies hovering in the center. Here you see the texture of the large-scale distribution of galaxies. I cannot resist introducing a few of the people who have made it possible to take such images. Here is Donald Shane, lower left, who in the 1950s spent 10 years of his life counting these galaxies. Here are 3 young graduate students at Princeton University, Jim Fryer, Ray Siniera, Mike Seldner, who turned that data into the map you've just seen. The data, a copy of it, sits still in my office. It is this pile of data sheets. Pause to consider that Donald Shane, working with his assistant Carl Wertenen, counted 1 million galaxies. Before high-speed computers, what do you do with 1 million numbers? Very little. Yet he took the data with such care that when high-speed computers came along, it could be turned into a map, and we had the deep pleasure of showing the map to Donald and asking him, "So, is this what you saw?" He laughed and said, "I was looking at this one galaxy at a time." Now you will notice this illustrates perhaps 1.5 law of cosmology. The universe is very clumpy. You see the clumps running across the sky. But you may also notice something new, or rather something old, that this part looks a lot like this. We will see that illustrated in even more detail if we look at galaxies that are seen further away, so we see structure on still larger scales. That may be done by looking at galaxies that are particularly prominent. This galaxy, whose image you've seen before, looks very dull and ordinary, just a gas of stars. But in the center, there is, and here is the center, a bright point of light and a jet of light running away from the center. An explosion in the center, whose source is not really understood well. It is thought that there is a black hole in the center, material falling in is squeezed very tightly and causes these jets. Their origin is for us not at issue at the moment. They exist, and sometimes they are very prominent. Here, this galaxy has suffered a really big explosion. This radio image shows a jet of very relativistic plasma going this way, a weaker jet this way, two plumes of plasma glowing in the radio. This is an image of this object at 6 centimeters wavelength. The scale is beyond our everyday experience by orders and orders of magnitude. The wavelength, something we'll never see with our own eyes, yet I trust you are as pleased as I am with this image of an aspect of reality we will never experience. For our purpose, the main point of this image is such exploding galaxies are very prominent. And here is the distribution across half the sky of the nearest 50,000 or so of these prominent galaxies, taken with the radio telescope, the VLA, in New Mexico, United States. You must ignore the hole in the center. The instrument couldn't reach that. You must ignore this hole. The sun was getting in the way. You must ignore this hole. The plane of the Milky Way galaxy is running along here and causing confusion. When you look elsewhere, what do you see? You see Einstein's vision. This is an aspect of research. Sometimes beautiful and simple ideas lead us to aspects of reality. In this case, despite all of the contrary evidence that existed back when Einstein introduced the idea, enormous courage, let us not even say disregard of the real world, to introduce that concept and to defend it, but ultimately to be proven to be right. A beautiful idea led us to an aspect of reality, the first law of cosmology. Let us go on to the second law. The universe is expanding. This can cause confusion. You are not expanding, nor is this room, nor is this solar system, nor is our galaxy. In fact, the nearest galaxy is falling toward us. But on larger scales, the trend is galaxies are moving apart. It is true, no matter which galaxy you sit on, you will see more distant galaxies moving away from you. I plan to give you an illustration of this expanding universe in a moment, but first I think we should again trace back to the history of ideas and discoveries. It begins very appropriately with Percival Lowell, who was born into a very rich, socially prominent family in Boston, Massachusetts, northeast coast of the United States of America in the 1800s. He augmented his family fortune by shrewd movements in the money market, then later in life returned to his first love, astronomy, built an observatory for the purpose mainly of looking for evidence of life on Mars. His memory is honored by astronomers for two great things. First, he chose to build his observatory at a very favorable site rather than one convenient to him. And second, he hired the very best people to build instruments for his observatory and to use the instruments. In particular, Slipher, who discovered an important property about these galaxies. Their light is shifted toward the red, as if they were moving away from us, the Doppler effect. You've all experienced the Doppler effect. You stand by the side of the road, you hear the cars rushing by, va-room. Of course, the pitch of the noise from the engine isn't changing as the car moves by. As the car rushes toward you, sound is being compressed and the pitch is increased. As moving away, the waves are stretched and the pitch decreases. The same with light. And the fact that the light is stretched toward the red is suggestive of the fact, we now believe is a fact, that the galaxies are moving away from us. It was Edwin Hubble on the left in this photograph who, during the 1920s, was discovering the law of regularity among these galaxies that I'll mention in a moment. And it was a young Belgian, Georges Lemaitre, who discovered the connection between Einstein's general relativity theory, the notion of a uniform universe, and these redshifts that Slipher had discovered and Hubble had mapped out. The year before the photograph you've just seen was taken, Lemaitre was at Cambridge University. Here is a note from one of his professors, A.S. Eddington. I certify that the Abbé Georges Lemaitre has been attending my lectures and pursuing his studies to my entire satisfaction. And and pursuing his investigations to my entire satisfaction during the academic year 1923-1924. The following year, he went to MIT, Massachusetts Institute of Technology, again in Cambridge, Massachusetts, United States of America, where he studied general relativity theory and where he heard a lecture by Edwin Hubble on this phenomenon of the redshift of the galaxies. He had the insight to connect that phenomenon with Einstein's relativity theory, which he was studying, to introduce the notion of an expanding universe. He returned to Belgium, wrote up his results in a journal, and awaited reaction. He got none. The establishment ignored him. He wrote to Eddington to ask if he might consider his article. Eddington ignored the letter. He wrote again, very pressingly. Eddington at last responded and recognized that Lemaitre had something fascinating here to reveal. We know that Eddington was very taken with this idea, and so was the rest of the community. Here is a copy of a letter addressed to, you see, Professor Willem de Sitter, Sterrenwacht, the Observatory, Leiden, signed Arthur Stanley Eddington. The middle part, and I should have remembered to notice the date. Can you read it? Yeah, 1930. He published his paper in 1927, 3 agonizing years before it was recognized. Lemaitre's address, apparently de Sitter had been asking. The following comment: a research student, McVitie, and I had been worrying about the problem and made considerable progress. So it was a blow to us to find it done much more completely by Lemaitre. A blow softened, as far as I'm concerned, by the fact that Lemaitre was a student of mine. Well, what that illustrates, of course, first is that if you do something great, you will win friends. But also, of course, we must admire Eddington greatly because Eddington immediately arranged to have Lemaitre's article reprinted in the premier journal, the monthly notices of the Astronomical Society of Great Britain. You can see that Eddington made Lemaitre famous. Here is a cartoon by one of de Sitter's comments, teasing slightly the great Professor Dr. Willem de Sitter on the results of a newspaper article, here quoted in a still famous Dutch newspaper. I will comment on the meaning of this curious symbol later. For the moment, I want to comment on how this illustrates the notion of an expanding universe. Imagine we live not in 3 dimensions of space, but in 2. We are ants that can crawl on the surface of this balloon. You'll notice that, apart from this small artifact, the balloon has no edge, no center to the ant. The ant may move in a straight direction and will find no edge, but of course come back to its starting place. Here's a finite universe with no edge, so far as the ant is concerned. Now imagine the balloon is being blown up. You must not imagine the individual galaxies, they're rather schematically drawn, are expanding, as I said. Imagine them as little discs of paper glued to the surface of the balloon in one spot. Now imagine the balloon is blowing up. You're sitting on a galaxy and look around you. What do you see? Wherever you sit, you see galaxies moving away from you. And furthermore, you see that the further the galaxy is from you, the more rapidly it's moving. That's the regularity Hubble had discovered back in the 1920s. And here is the regularity as it was established in 1905. Out to redshift, already 10% of the velocity of light in 1935, one sees this linear relation, apparent recession velocity proportional to distance. That's the expanding universe. We come now to the next law of cosmology. How do you know it's really expanding? The picture hangs together and it fits general relativity theory, but general relativity theory is not well tested. You have to test this notion of expansion against empirical evidence. And among the earliest pieces of evidence is the evolution of the galaxies. Galaxies seen at great distance are seen as they were in the past, because of course it takes time for light to travel from there to here. The more distant the galaxy, the younger the galaxy is, because the longer the time has taken for light to get from there to here. That means that we have a critical test. Galaxies seen at great distance ought to look young. I remember early in my career in cosmology encountering this issue in connection with the steady state theory of cosmology, invented by Fred Hoyle, Tommy Gold, along with Herman Bondi. And I remember here is the explanation of this steady state cosmology, the basic idea. Yes, the universe is expanding, but there is continual creation of matter that collects to form new galaxies to occupy the spaces vacated by the receding galaxy, so that the universe is in a steady state. Here, one of the proponents of the steady state theory, Jeff Burbidge. This photograph taken in the 80s, but I remember meeting him in the early 1960s and his shaking his finger at me and saying, when astronomers look at distant galaxies, they see galaxies that look very much like the ones nearby. Why don't you see the evolution your theory predicts? Isn't this observation really more consistent with the steady state picture? That was a very good point, and one that haunted me for years. I suspect drove much of the research I was doing at that time. But we have now a fairly direct answer. Here is an image of the sky taken with the Hubble Space Telescope, the so-called ultra-deep field. This is a section of the sky 1 millimeter by 1 millimeter at my arm's length. That little speck of the sky is here imaged. We will see it in a larger scale here. And the telescope was pointed at that image for days at a time to accumulate the deepest possible image of that bit of the sky. What does one see? Relatively nearby galaxies. A few stars, but very few. This is a tiny field. You see intermediate-sized galaxies that are intermediate distances, and you see in between way back in time because you're looking way out in space. And among those galaxies, as you look at the more distant ones, you start to progressively see messes such as this. Here, a fairly small galaxy of stars. Here, a plume of atomic hydrogen, more massive in its dimensions than anything seen nearby. Here is direct evidence for this new law of cosmology. The universe has not always been the way it is now. The universe used to be younger than it is now. A striking concept, but here it is visually demonstrated. The next law of cosmology: space is filled with radiation, thermal radiation, at a temperature of 3 degrees above absolute zero. You're all familiar with thermal radiation. Put your hands near a hot source, perhaps a fire. Your hands are warmed. That's thermal radiation. You might be familiar with the thermodynamic law that says at statistical equilibrium and at a given temperature, the intensity of that radiation at each wavelength is determined only by the temperature. I think that the notion that the universe was filled with this radiation at high redshift in the early universe was introduced again by Georges Lemaitre, shown here, a couple of years after he made this, I think, elegant statement. The evolution of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes, and smoke. Standing on a well-chilled cinder, we see the slow fadings of the suns, and we try to recall the vanished brilliance of the origin of the worlds. The implementation of this notion, the vanished brilliance, was made by the other person in this figure, Richard Tolman, at the California Institute of Technology in California, in the United States of America, who proved that if a homogeneous uniform universe is filled with this thermal radiation, Then as the universe expands, the radiation cools, but it keeps its thermal character. That is the key thing. This cooling radiation was used by George Gamow in the 1940s to build the first theory for the origin of the elements, as cooked during the early phases of this hot expanding universe and left as fossil debris as the universe expanded and cooled. His theory for the origin of the heavy elements has been translated. It now applies to exploding stars, not the expanding universe. His theory for helium stands. This is the way helium in the bulk was produced in our galaxy as a remnant of the universe when it was very hot, as a thermal cooking of hydrogen. Here is my thesis advisor, Bob Dickey, Cambridge, 1945, with Annie, their firstborn, Nancy, now an academic, a microbiologist. Bob Dickey was at the time, again, in Cambridge, in Massachusetts. I've mentioned the name before. Here is a photograph of a building built during the Second World War for war research by Bob Dickey and many others. Here is a photograph of Bob Dickey on top of that building in 1945 with colleagues and with one of Bob Dickey's inventions. He called it a microwave radiometer. It is just the object for detecting thermal radiation. Here is a demonstration Bob made of the fact that this device detects thermal radiation. Here is a sketch of the skyline of Cambridge, Massachusetts, where MIT is located, as it was in 1945. It was at the time a somewhat industrial city. Here are smokestacks. Some of these smokestacks were warm. Here is a chart recording showing what happens as the instrument is scanned along the horizon. You see the deflection each time the instrument passes a warm chimney. It is detecting thermal radiation. Here is a photograph of another rooftop. 20 years later, this rooftop in Princeton University. In the left, coyly hiding, my dear friend and colleague David Wilkinson, but you'll hear more later. Here is a Dickey radiometer, which he had built with Peter Roll at the suggestion of Bob Dickey. Here you see a clearer view, slightly, of David Wilkinson. Here you see Peter Roll coyly hidden behind a Dickey radiometer built to search for this radiation. Here you see another experiment some 30 miles away. Is it Bob in Holmdel, New Jersey? Bob Wilson on the left, and it's my great pleasure to welcome here Bob in the front row. On the right, Arnold Penzias. They had set up an experiment to look for radiation from our galaxy. The conditions for that experiment were just such that they were led to build an instrument with the capability of the instrument that Wilkinson and Roll had built at Princeton. Here we see yet another photograph of MIT, three very distinguished and serious professors of physics at MIT. The middle one, Bernie Burke, knew about both the Princeton experiment and the Penzias-Wilson experiment. He was the one who said, you two guys ought to get together. When they got together, here was the result of the meeting. Arno and Bob had a detection of radiation that they couldn't interpret within their experiment. They detected radiation, didn't know where it was coming from. The Princeton group was looking for radiation of the kind that Penzias and Wilson had discovered. Fortunately, the Princeton experiment was at a different wavelength. A few months later, their experiment was completed and they had a second point. Now, here is the point of this whole game of thermal spectrum. One point determines an intensity at a given wavelength, that determines the temperature, and that predicts the intensity at all other wavelengths. And so, you see, the fact that the two are consistent with this thermal black body spectrum was great encouragement. I've been asked on many occasions, what was the feeling at Princeton when word came that Bob and Arno had discovered what Princeton was looking for? As best I recall it, it was one of relief. The Princeton group was looking for something wildly speculative. Would nature ever be so kind as to show us this radiation? Now, of course, we didn't know nature had shown us thermal radiation just from this check. But the great encouraging fact was Bob and Arno had shown us that there's something there to look at, so that the experiment became positive. Great relief. To check that this is really thermal radiation, one has to measure out this curve. That has been done. The solid thin curve is the theory. This thick curve is not a theory, it's a measurement. Spectacular accuracy. These are other measurements at longer wavelengths. I'd like to show you the groups of people who have made this measurement over the peak. Here is one group, the Cosmic Background Explorer, COBE, so-called. Here is David Wilkinson, instrumental in getting this operation together. A US group working on this project for 14 years. Here is a group in Canada, University of British Columbia, led by Herb Gush, and here his two colleagues, Mark Halpern and Ed Wishnow. These people had been working for a decade on their experiment. By one of these coincidences that will happen in science, the two groups completed their measurements within a month of each other. The fact that the measurements were consistent and consistent with the thermal background was enormously influential to us all. First, consistency between the two groups showed us it can't be an accident, fluke somehow. It's real and consistent with our ideas. I also, you might notice this is not the best image, best quality. Nonetheless, I treasure it. I treasure it. Because, well, these people did something great. They made a magnificent measurement. And therefore, I can't touch them. And so I can state what I think whenever I see this, which is, if you had only this image to judge by, if you knew only this, you didn't know that these people had done something great, would this image inspire confidence? Which, of course, illustrates why I shouldn't invite you to ask such questions. Spectacular, and here it is again, tangible evidence. The universe as it is now is transparent at these wavelengths. It's incapable of forcing radiation to relax to this very specific form. The only way we can understand this is to say the universe has not always been as it is now. The universe must have been at one time in a dense, hot state when it was optically thick, could relax to equilibrium. This then is a fossil remnant of the universe when it was hot and dense and young. Tangible evidence that the universe is not forever. Our universe is a transient thing. Let's move on. The clumping of matter. Galaxies, matter clumps. We've seen examples of that in galaxies, in groups and clusters of galaxies. Why is it? It's now considered obvious. It's gravity, pulls material together. 40 years ago, when I started this game, it wasn't at all obvious, and there were some clues. I remind you of this image of the way the galaxies are distributed. I would ask you to try to bear in mind what this image looks like as we compare distributions of other objects. Consider the distribution of nesting seabirds on the left, where you will notice that no bird will sit closer than one pecking distance to the next. But otherwise, they want to pack in as closely as possible, I suspect because they want the predators to eat the ones at the edge. Compare that to the distribution of people on a beach. This is Coney Island on a not very crowded day. Compare the differences, and compare also the distribution of sand in this beach, where I want to imagine that the last tide has smoothed out the sand and then people have walked through it. We will now introduce a small statistic that will measure the properties of these distributions and compare them. The statistic is simple enough. Stand on each particle in turn, go a distance r, and in a volume element, delta V, ask for the probability that you find another particle. That probability ought to be proportional to the volume element. Double the volume element, you'll double the chance. The constant of proportionality is conveniently a number density, and then 1 if you had a random distribution, and then plus a correlation function. Now we can sketch out what the correlation functions for these distributions look like. For birds, the correlation function is -1 because you will not see one bird close to another until you get to pecking distance. Then the correlation function rapidly rises to 0 because the birds don't care where they are after that. The distribution you saw of birds might remind some of you of a distribution you see in solid state physics. It's a glass. And very different from the distribution of sand on the beach, where on the beach, when the sand is distributed from being level, one has knocked the sand down in one place, piled it up in another. That means that the correlation function has a negative part, anti-correlation, because where you find sand, you find at a characteristic distance away the absence of sand, because that's the sand you got in this heap came from over here. On the other hand, if you look at the distribution of people on a beach, you will see a curve that looks rather like so. People, despite all evidence to the contrary, like each other. People like to be together in clumps and groups of groups. And as it happens, galaxies are the same way. None of this evacuation. Instead, the correlation function is always positive or very close to it. That has a simple interpretation, simply but I think deep. Imagine we start with a universe that's almost exactly uniform but has the slightest of imperfections, a little excess mass here. We recall what gravity says, that the acceleration due to a mass concentration varies inversely as the square of the distance away. Since we are only perturbed slightly from uniformity, that acceleration drives a velocity that is proportional to the acceleration, proportional to 1 over r squared. The area within which sand is moving at distance r, or material, is proportional to r squared. The product is the rate at which mass flows through this surface, and you notice it is the product of this number with this, which is to say it's independent of the radius. Very deep point. When gravity draws things material together, it increases the density only where the density is already high. It doesn't increase the density here because the same amount of mass is flowing through each surface. That is characteristic of the galaxy distribution and what has forced us to believe in the early days that it is gravity that forced the development of the clustering of matter in the universe. Here are early days at Princeton in the work on cosmology. Here is Bob Dickey, my teacher, my professor of continuing education the rest of his life. Here is David Wilkinson, my close friend and colleague for many years. Here is my first graduate student, Jer Yu, now at City University of Hong Kong, and again, I believe somewhere, oh, there you are, Jer, good to see you. Do you recall your thesis, Clusters of Galaxies, Their Statistics and Formation? This was the beginning of the studies that I've just described. 1968. I was interested to read, this work was supported by the United States National Science Foundation and by the United States Office of Naval Research. Why did the US Office of Naval Research care about galaxies? Of course they didn't. In those days, research was somehow more open. The Navy spent an infinitesimal amount of its budget on pure science in the hopes that something might come of it, and that something of that might come to them. Strictly speculative, the investment is minuscule, why not do it? Things have changed, bureaucracies hardened, it's no longer acceptable. The Navy Office of Naval Research may not support us. It's too bad. It's too bad. But let us go on to a paper, Jer. This is your life. You remember 1970, you had moved to Goddard Space Flight Center, New York, near Columbia University. Again, NASA supporting you, National Space and Atmospheric Agency, doing research on distant galaxies, research that at the time you might have thought will never come to any use, even in pure science. The issue to be discussed, if, as the pattern of clustering I've described indicates, gravity drove the formation of cosmic structure, then there is an instant implication and one that can be computed. That gravity must disturb the radiation that is filling space. And the disturbance to that radiation may be computed under the assumption that that is what is causing the galaxies to form. The disturbance may also be measured, at least in principle, and by the measurement one may check whether indeed it is gravity that drove the formation of structure in the universe. This is the paper that laid the foundation for the analysis of measurements of small disturbances to a uniform distribution of radiation. Here is a paper some 10 years later. By this time, measurements of the degree of irregularity in the distribution of radiation were becoming very tight, and the irregularities were not yet showing up. Since I still like the notion that gravity is what drives formation of cosmic structure, I introduced a paper, a model, in which, by making suitable assumptions, I was able to find a self-consistent picture that is the simplest of all possibilities for the way galaxies formed. This simplest of all possibilities produced disturbances to the radiation distribution small enough that one could still imagine that future measurements, more precise measurements, would reveal the disturbances and perhaps check this model, perhaps rule it out. At last, we have had detection of this radiation fluctuations. Here is a map of the variation of the temperature of this radiation across the sky. You must understand that this radiation, this map is showing the fluctuations around the mean temperature. The departure of the temperature from the mean is only 1 part in 100,000. Minuscule, but yet measured. This measurement was made with a satellite specially designed for the purpose. The lead designer, David Wilkinson, the name of the project, initially called the Microwave Anisotropy Probe, was changed to the Wilkinson map because, alas, after a decade and a half of struggle with cancer, David died, but not before he had seen these data and the wonderful fact that they agree to spectacular precision with the theory. I don't want to go into any of the details. I only ask you to notice this is a pretty picture that has a curve, the theory, and dots, the measurements, and that they're in exquisite agreement. Again, nature has been spectacularly kind to us. That model I introduced almost out of pique to show that the notion of gravitational growth of structure is still viable. And of course, I chose the simplest of all theories, is the way the universe chose to operate. It's curious that these things happen. There are, on the other hand, complexities. The universe may, on the one hand, satisfy us with simplicity, and on the other, startle us with complexity, which means, of course, we're only making an approximation, successive advances in understanding. This was mentioned in the introductory remarks. The interpretation of these measurements requires a very curious arrangement. You and I, and planets and stars and galaxies, at least the visible parts, are made of what goes by the name, the jargon is, baryonic matter, about 5% of the mass of the universe, about 20% dark matter. I'll mention it briefly in a moment, and about 75% something else that is given a fancy name, dark energy, to describe the fact that we don't know what it is. Let's look at a little of the aspects of these mysterious dark components. Here is an image of a galaxy without a disk. You've seen it already twice. The optical images, this is the way the stars are distributed. This is an X-ray image taken above the atmosphere. We know that these X-rays are coming from hot plasma. You see the lines from common heavy elements, heavily ionized. You see that the plasma cloud surrounds the cloud of stars. One can measure the density and the temperature of this plasma. Knowing that, you know the pressure. Knowing that, you know the gravity required to hold this plasma in place. The gravity indicates that there is considerably more mass out here than is present in the stars, dark matter. That's not at all surprising to think that there might be forms of matter that we're not capable of seeing. Why should the universe be so constructed that we can see its contents? No guarantee. We require then dark matter. Through arguments that I think it might be too tedious to detail that were mentioned, we can be pretty sure this is not the baryonic matter of which you and I are made. It's some mysterious new form of matter. What is it? There are lots of ideas, and there is a great opportunity for you all. Tell us what that dark matter is. Meanwhile, let us go on to dark energy. I have here to remind you of a bit of a historical development. When Einstein introduced his general relativity theory and then his notion of a uniform universe, he found he had a contradiction. The theory did not fit the model. That is because he took it as obvious and given. The universe is forever. The universe is static. He didn't even ask himself whether that makes sense or is required. It's obvious. Of course the universe is forever. Surely. But of course it isn't. Because he had assumed the universe is forever, he had an inconsistent theory. He patched up the theory by introducing what was then called the cosmological constant, is now called dark energy. It's a change of name that only hides the fact that we don't know what it is, but that has the property that it is repulsive, it pushes. And so in Einstein's universe, gravity is trying to make this balloon shrink, the cosmological constant is trying to push it apart, and in Einstein's universe, the two are in equilibrium. It was Lemaitre's great discovery that the equilibrium is unstable. The slightest touch, and the universe will either expand or collapse. And of course, the observations pointed to the notion that the universe is expanding. That's the origin of this comment taken from the Dutch newspaper, who, however, blows up the ball. What makes the universe expand or swell up? That is done by the lambda. Another answer cannot be given. Lambda is this symbol and is Einstein's notation for his cosmological constant. In the picture de Sitter had accepted at this time, the universe began as Einstein's equilibrium, but unstable equilibrium. A small disturbance caused the universe to expand, done by the lambda. It was soon recognized that if the universe is expanding, it might make logical sense to imagine it was never in equilibrium. It expanded from a dense, hot state, as all the evidence now shows very clearly. If that's the case, lambda is not needed. When Einstein in 1930 recognized that the universe might be expanding, his immediate reaction is, away with the lambda. And for the decades following it, most people said, Einstein surely is right. This lambda is unneeded, inelegant, unwanted. It's superfluous. It's not there. It's ugly. But there were problems to the contrary, and they were recognized or rather introduced first by Wolfgang Pauli in the 1930s, compared to what the observations would allow. As Pauli famously remarked, it would cause space to curve up into such a small ball there isn't room for the moon. Ridiculous. It was Yakov Zeldovich, the great Soviet physicist, shown here with his wife in a conference in Balaton, enjoying himself, they both are clearly, who pointed out that the vacuum energy density of the vacuum, the quantum vacuum, although of an absurd value, does have the curious property that it acts just like Einstein's cosmological constant. The great challenge was raised. We now, as was indicated, require, to account for the evidence I showed you, the presence of that cosmological constant. The only problem is its value is wrong, according to the estimates of Pauli and many since, by a mere 100 orders of magnitude. Otherwise, all its properties are appropriate and correct. You see the spectacular challenge open to all of you. A Shaw Prize in the offering. Account for that factor of 10 to the 120 difference between what quantum mechanics says and what cosmology says. Bizarre to consider it, isn't it? On the one hand, I have been boasting about the great triumphs of research in cosmology, and it's not idle boasts. Those advances are real and substantial. And yet, the theory is riddled with an enormous hole. That, of course, is the nature of research. We make advances in successive approximations, and typically, when we make a great advance, we lead ourselves to newer questions to be addressed. Well, here it's stated, the first law of physical science. I would claim nature operates by rules we can discover. It's not obvious that that should be the way it is, but experience shows yes. Nature operates by rules we can understand. Important to emphasize in successive approximations. Of course, it's obvious along a path that you cannot predict, no clear direction. You make discoveries that lead you down the path. Furthermore, it's obvious the path cannot end, because we can only validate our notions experimentally, and experiments have only finite resolution. We will never know, if we have reached an ultimate reality, whether even such a concept exists within physical science. We can only make successive approximations. I've illustrated this path in an example, the discovery of the expanding universe. Recall the tortuous route it took. Einstein's bold, not to say reckless assumption, yet validated. Einstein's lambda, rejected by the greatest figures of the day. Pauli thought it was absurd, yet present. And of course, by the validation of the notion of an expanding universe, the introduction of new challenges, discover the nature of the dark matter, reconcile the quantum vacuum energy density with the cosmological model. Deep puzzles right before us. And I think it's not at all difficult to make the prediction that when finally one of you has resolved these puzzles, that you will have presented us with new puzzles for the generation to follow you. Thank you very much.
Thank you very much, Professor Peebles, for a most fascinating story of how we human beings have come to understand, obtain the present understanding of our universe. I think we have quite a bit of time. Perhaps we could take some questions from the audience. Questions from the audience? Yes, Professor Lai, please. To the microphone.
In one of your transparencies, you show the excellent agreement of the theoretical curve of the black body radiation and the experimental data. But I noticed that all those data are on one side of the peak, on the long wave length side. Why there are no data for the short wave length region?
I hope you noticed. Would it be possible to show that figure again? Very important to notice. Well, I don't know how to. Is it possible? Maybe we go back. I perhaps was too careless in drawing your attention to the key point of that figure. Here you have a little review. Whoop.
Just a minute. May we have the screen down, please?
What have I done with it? Oh, no. Yep. Here it is. Here it will be in a moment. It's rather exciting, isn't it, to see it rise and come into view. Now you will notice from here to here, this is a measurement. This thick line is a measurement. Measurement. It's so astoundingly precise that you can't tell. This is perhaps poor. We should make this a dashed line. This is the theory. This is a measurement. Yeah, it's misleading. But and isn't that stunning? Precision science. It's just gorgeous. Notice the number of orders of magnitude in wavelength and energy. Now, of course, over here, emission from dust in our galaxy obscures the view. And over here, radiation from exploding galaxies, radio radiation, prevents measurements at longer wavelengths. This is almost as good as can be done. There are experiments discussed to improve the measurement around here, which can be done. There are ideas about how the interaction of the radiation with matter may push this up a little bit. That would be lovely to see. I think this part we will never see. It's buried in emission from dust in our galaxy.
Thank you. Is there a question over here? Yeah, Professor Chen, please. Yes.
Okay. Professor Peebles, would you share with us your best guess? What is the nature of the dark energy?
My guess is it's a deep, deep mystery. The hope of many for many years has been that there is some symmetry that forces the dark energy density to be zero as an identity. That would be a neat solution. but a symmetry that forces the dark energy to be not exactly zero, but spectacularly close to it is so ugly that I can't hope for it. And so my secret dream is simple, that indeed there is a symmetry that forces the vacuum energy density to be zero identically. Now, it's easy to introduce into the standard model for physics scalar fields with self-interaction potentials that will again behave very much like the cosmological constant. They will, though, have a happy property that may be discoverable. Typically in these models, as Bharat Ratra, a good friend of mine and colleague 15 or 20 years ago, discussed, the energy density is not exactly constant, as a cosmological constant would be, but is rolling slowly toward its natural value, zero. That rolling towards zero may be detectable, because of course one observes the universe at different distances, at different ages, and if observed, it would be a pretty good signal that this dark energy is not vacuum energy density, it's the energy of some field. There's absolutely no guarantee that it will ever be checked, and still less that it will be established to be the case. On the other hand, there's never been a guarantee that we can make the next advance in physical science, but we've been doing very well for the last several hundred years, and maybe we'll be lucky again, and nature once again will provide us with a prime hint. A prime hint such as that. Maybe we'll be lucky.
Okay, I believe there's a question from upstairs.
Well, hello. Well, I would like to make some comments first, if I may. The first one is, do we know the mass of the universe? And if we do know that, then clearly we believe in the conservation of energy, conservation of mass, as very fundamental laws of physics. And what I really would like to say is that there is no existing physics, laws of physics within the grasp of human imagination or laws that can actually bring so much matter into a tiny area some 14 billion years ago and let go in this unimaginable violence which we call Big Bang, as you know, Fred Hoyle called that. We have no evidence for Big Bang. And my second comment is that the cosmic background radiation, and for that it doesn't necessarily originate from this fossil energy, as we call. We still have problems with dark energy, dark matter. They could be originating from that. And the redshift itself, well, who knows? It could be just originating from galaxies revolving around some gravitational fields. So really the unification of all these laws or concepts of gravitation, dark energy, dark matter, and the fact that we have to really question the fundamental problem of this Big Bang will bring us closer to the realities that you mentioned.
Thank you for those stimulating remarks. First, very important point to make, the words Big Bang are very misleading. I nowhere here said stated the origin of the expanding universe. Nowhere here did I talk about a bang in the sense of a localized explosion or an event in the sense of an explosion. I am talking about evolution from one state to another. I have argued from dense and hot to low density and very cold. Not a Big Bang. Second, with respect to the mass of the universe, it's not defined, and in fact, within general relativity theory, mass is not conserved. Energy is not conserved. It's rather shocking. You've spent, if you're a student, all those years conserving energy, and Einstein didn't. But that's the way it is. The theory does not conserve energy. It does conserve energy locally, but globally there is no energy integral. I do insist, though, that within general relativity theory, the picture of a universe that evolved from a dense hot state to the present is mathematically consistent. And although one has for years argued about the possibility, could this radiation have come from the stars or from the dark matter, or perhaps even the dark energy? Always a possibility. But the deep challenge for you, if you wish to defend that idea, is this spectrum, so spectacularly close to what would be predicted in a universe that expanded from a dense state to the present. And remember, there's not just one piece of evidence for this expansion. I stressed the aging of the galaxies. I think the picture is pretty tightly cross-checked and coherent.
Right. Other questions? Over here, please. Yes.
Professor Peebles,
yes.
you mentioned that the distance between galaxies are increasing, whereas on the other hand, the distance within galaxies are fixed. So what caused this difference, and where should be the demarcation?
Gravity causes the difference. Our galaxy is gravitationally bound. The transition is at about 24 million light years. It's measured. On smaller scales, the galaxies are either gravitationally bound or coming together, starting to depart from general expansion. An example, the nearest galaxy, the Andromeda Nebula, whose image you saw, is coming toward us. Theory says in the past it was moving away, but gravity is causing the recession velocity of that galaxy to decrease. It has now turned around and is starting to fall back toward us for the first time. This is the gravitational growth of structure. Our little system of galaxies, Andromeda, us in the Milky Way, and a few others, will eventually be a gravitationally bound system. It isn't yet. It's just forming. But one can, by doing statistics on the positions and motions of the galaxies, determine this characteristic radius I mentioned, outside of which galaxies typically are moving apart, inside of which they're either falling together in concentrations or have already fallen together.
I believe there's a question upstairs.
Professor Peebles, doesn't the second law of thermodynamics show that the universe cannot be forever and that it must change?
Yes, that is an excellent point. It wasn't recognized by Einstein. He knew about the second law of thermodynamics. He never paused to reflect that his static universe is inconsistent with thermodynamics. You understand our universe is okay. It's one shot. But indeed, you're right. A static universe is inconsistent with standard physics.
Thank you.
Okay. This question over here, please.
Yes, Professor Peebles. I realize that you make a comment about the 0-point energy being made out of mass, and I realize that there's something called a Campbell's theorem that says that, for example, mass in 4th dimension can be made to be equivalent to a flat 5-dimensional space-time, and so it seems that if you introduce extra dimension, that might be able to explain away the 0-point energy, and that's one. And for two, there are people who are modeling the dark energy without using a scalar field. For example, they use extra-dimensional FRW equations. So it seems that in principle, extra dimension can be used to take care of a lot of these problems that you've talked about. So my question is that, do you believe in extra dimensions? And because it seems that in your recent work, you have not preferred to use extra dimensions.
Yes, thank you for those remarks. I still believe that the challenge understanding the dark energy is direct and dramatic. Of course, we are not without ideas on how to address the challenge. One of them you have mentioned, extra dimensions. Do I believe in extra dimensions? Of course not. Because no one has shown me experimental evidence of them. Do I disbelieve? Of course not. It's an open issue, which is to say, work for the next generation, work for you, your students. Is this the most promising line of attack? I can't even judge that, although I must admit I don't know of many others. I have not seen a paper in which the extra dimensions have been used explicitly and cleanly to solve the issue of the vacuum energy density. Yes, the ideas are floating around. Perhaps we will read in the media of the ideas coming to fruition, but I haven't seen it yet. I certainly would not rule out the possibility that that's the directions people will be taking.
I think there was another question back there. Yes, please. Could you come to the microphone? Yes.
First of all, I'm sorry, my English is not good because I don't have university education, nor I don't have the education in English. That's maybe, so that maybe some terms, what I mentioned are not so exactly what I mean. And to give my comment is that may I suggest that the dark matter and the dark energy, would that be possible that comes from the center of the galaxy? The center of the galaxy that releases the matter is a substance of release of mass. And this also gives a simple explanation for why our universe is still expanding. And the black hole, the hidden matter in the center of the galaxy, may we think that is an X dark hole that the matter that aggregate. And when the matter that exceed its singularity that could suffer and then give an explode. And this is a sustained motion, action. That's my question.
I'm not sure I followed it entirely, but perhaps we could start a little dialogue if I could. This modern system could move more quickly, couldn't it? We need some better technology to allow me to go backward more quickly. I don't know why I can't go to slide number 5, but you will be patient. We're getting close. No. I would really like to show an image that is back here somewhere. I'm sorry for this. Do you recall this? In the center of our galaxy, there is a mass concentration. Mass 1 million times the mass of the sun. Very dense, very compact. It is thought to be a black hole. That is a common phenomenon. In this galaxy, there is a bright spot at the center. There is also a tight mass concentration there. This concentration, 1,000 million solar masses. It is thought that this black hole is accreting matter, and that the accreting matter causes an explosion. The details not understood, and perhaps yes, the centers of galaxies are active and produce material that rushes away from the galaxy, as here. Now we might ask, could this be the source of the expanding universe? That is not anywhere near the current idea, and I do not see how to implement it. Although this object in this galaxy also is very massive, its mass is only 1/1000th of the mass of the galaxy. It will eject energy, and it will lose mass thereby, but it's not going to inject very much energy. And so within our present understanding, I see no way to turn this energy into any useful form, such as an expanding universe. It's generally thought that it's going to make cosmic rays, but nothing very substantial for the expanding universe. I don't know how to go any further along your line of thought. I don't know how to go any further. This is physical science, which means we never have absolute truth. I have presented you what seems to be a consistent story. I cannot guarantee you 100% that this is the way it is, only that the evidence strongly and coherently points in this direction.
I think we have time for a couple more questions. Yes, there's one up there.
Professor Peebles, you have told us that the universe is expanding. To me, it is intuitive that something expanding should have a boundary. So my first question is, does the universe have a boundary? And because it is very easy to imagine that if a road, we come to the end of a road, there is a wall. So when we come to the end of the universe, what is it? Because it is very difficult to imagine that something, that there is lack of space. So what is it?
Excellent, excellent. So may we come back to the notion of a balloon? Which direction are we going for the get to the balloon? I've forgotten already. It is this direction. If the universe, where is the edge of the road? Where does the universe end? Where is the center of the universe? Now, this may be very misleading. This balloon has a center. It's right there in the center. But remember, we are supposed to imagine in this intellectual exercise that we live in 2 spatial dimensions, not 3. This center of the balloon is not in our world. It's not there. We can't. It's not for us. We live on this surface. And you recall how I said this universe, it's an example of a universe that is finite but has no edge. I take the road in this direction, I come around, come back up, and voila, I'm back home, never having encountered an edge. This is one model for our 3-dimensional universe. You must stretch your mind to a 3-dimensional sphere, if you wish, curved into a 4th dimension. In fact, that wish is not required. There is no reason to think that there is space inside or outside our universe. This is only an analog that helps you think about things, but I hope it illustrates the point. Our universe may have a finite size, yet no end of the road. You mentioned another question first, but I didn't catch the key word. My intuition says, what were you asking? Does the universe have a boundary? Aha, boundary. No, not that we can see. It's universe all the way. Of course, there is no guarantee that there is not a boundary. But only a boundary, if it exists, must be beyond any distance we can see. You will notice that we can see only a finite distance because the universe has a finite age. What's beyond that is for speculation or deeper theory that might indirectly lead us to a better aspect of reality. What we can observe has no edge. It's galaxies all the way. That was illustrated, I think, in that beautiful image of the Hubble Ultra Deep Field. Here we are, looking out into space, and of course back into time, from relatively nearby galaxies only thousands of millions, tens of thousands of millions of light years away, to galaxies that are more and more distant, until the most distant galaxies in this image are, according to the theory, at the edge of what we can theoretically see. And it's galaxies all the way. No edge.
So do you mean that if the space is curved, then at some time we can see our own image coming back 1,000 years?
Alas, I do not. If our space is curved, then the theory says it will take too long for light to get around. So we will not see the back of our face. There are other models in which we might expect to see ourselves, so-called periodic universes. My guess is they're nothing but mathematical tricks. Furthermore, I'm a little nervous about giving you the analogy of a balloon because it suggests that our space is curved rather than that our space-time is curved. The best evidence is that our space is pretty close to flat, although indeed space-time is curved. Space sections close to Euclidean geometry.
Okay, I think one final question. Yeah.
Professor Peebles, I wonder your work shows some discovery of curious facts, but I wonder whether your work have any significant impact on astrophysics or in other fields of physics. Yeah, thank you.
Physics is a united field. I include in it all of quantum physics, condensed matter physics, fluid physics, biophysics, astrophysics, cosmology. It's one subject, really, and the subjects do interact very strongly. So discoveries in one branch of physical science influence somehow all other branches, sometimes very loosely, sometimes very directly. Certainly the advances in cosmology have had profound influence on our ideas about basic physics. A simple example, the number of neutrino families tightly constrained by consistent stories for the evolution of the early universe, more loosely by the fact that if we did not have cosmology, particle theorists would not be nervous about the vacuum energy density. You know that within quantum physics there are divergences that are conveniently hidden by saying, well, we can only measure exchanges of energy, not absolute values of energy. Without cosmology, there would be no difficulty with the quantum vacuum. So it's an enormous number. Who cares? An example of the influence of one field on another. This is a united subject.
Well, I'm afraid we have run out of time. If some of you still have questions, a good place to start is to take the course PHY 4460, offered by the physics department in the second term. Let us thank Professor Peebles for the wonderful lecture and for the opportunity for the audience to interact with you. I hand this over.
Thank you, Professor Young, and thank you, Professor Peebles. All of the audience were very excited here, so may I now invite our Vice Chancellor of the Chinese University, Professor Lawrence Lau, to present a souvenir to Professor Peebles. Professor Lau, please. Can I have Professor Lau and Professor Peebles on our stage again? And we'd like to invite Professor Young to join us again, as well as Professor Cheng, our college head, for a group photo.
We need to take a